So let us now add the backward part for the softmax layer and also for the entropy part. Just like to remind you on the structure of the output from the softmax layer. So we have the probabilities assigned for each separate observation. And for every observation, we have to calculate the Jacobian matrix because that's the inner derivative from the softmax layer. And then we have to multiply this with the d values, which is the outer derivative from the layer which is beneath the beneath the softmax layer. So let us just go to the softmax class and let's add the backward part. And of course we use self again. And here are the d values as an input, which is the outer derivative from the layer which is below the activation layer. So in order to calculate the Jacobian matrix, we have to take every entry for every observation from the probabilities that we calculated already and saved under self output. And as I described earlier, we would like to do this in the loop. So therefore, we just now iterate over the output here and also over the d values. And since we want to have the probabilities from every single observation, I want to call this variable single output. And for the d values, I want to call it single d values. And then we want to run it for self output. So these are the probabilities, and then d values, which is the input that came from the layer below, softmax layer, so the outer derivative. Use enumerate because we want to evaluate over the content of those matrices and vectors, but we also want to get the index I. And if we want to evaluate over two vectors or two matrices, then we have to use zip. And now we are able to do everything at once. So by the way, this line actually draws the line for a sheet of paper. So if you in principle would like to print out this this code for whatever reason on it on paper, this is just the line that marks the edge of a sheet of paper. What I usually do is that so if the code doesn't look too lengthy, I add a line break, which you can actually do with this slash here. Sorry. And then the code looks a bit more compact if you like, but you don't have to do that. Right. By the way, that's also interesting. So this error message here comes because there's an empty space after the line break. Then we just remove the empty space and then the line break is gone. All right. So what we have to do now is to calculate the Jacobian matrix. And call it Jacobian matrix. So we have to calculate the Jacobian matrix. And how do we do that? So there is the first part of the derivative, which is the diagonal matrix. And we can achieve that by using diagonal flat. So we take the single output and it turns it into the diagonal matrix. So I also want to remind you on on that. So let's actually show that directly. So we have a single output, and this would be, for example, the output from the activation. And let's say we just want to take a look at the first row, all columns. Then we get a single output. And then if we just say diagonal is flat, then we get a single output. It's a diagonal matrix. So that's the first part of the derivative from the Boltzmann distribution. Then we have to subtract the matrix itself, but squared. So we can just multiply the matrix with itself by using np dot, and then multiplying single output with single output transposed. And also here want to show you the structure. We have to make sure, of course, that this makes sense. But however, we actually want to have a matrix. So what went wrong? And if I take a look at the shape of single output, this went wrong. And again, we have to take care about this particular structure we have in Python. So we can apply a trick and we can actually reshape it. So we can say single output equals single output reshape. And then we can, for example, turn it into, so since we have a column vector, we actually want to maintain the structure, and then we reshape it like this. And if we take a look at the shape now, it has the correct shape. So in order to make that work, we have to reshape it. And that's why we should add this before we calculate the Jacobian matrix. And now since we reshape it, we can run our matrix multiplication again. And this time we have a matrix. So that's something you always should test before you just run the code, because it would not necessarily create an error message, because you just would subtract just a number from a vector or a matrix, which of course is always possible. So you would not get an error message even. And also here, I want to just add a line break, and also here, be careful with that you don't get this error message here. Okay, so that creates or calculates a Jacobian matrix. And now we have to multiply the Jacobian matrix with the outer derivative, which is in single values. So we have a matrix now that we multiply with a vector, which returns a vector again, and we can put this into our matrix self, the inputs. So the inputs again will be the output from the backward part. We feed it in as an input, so as d values for the layer which is above this particular layer here. And that's why we need index for, because we know we want to put this in row number I, and then we just perform the dot product. So we just multiply the Jacobian matrix with single d values. So that's it. The only thing we have to do is pre-allocating self the inputs. So we, of course, going to do that before we start a break. And we can do this with np zeros or np empty, but we can also do this with empty like. And we discussed earlier, it should have the same structure. So we can create a matrix with the size of the values. So in principle, you could also use NP zeros. Then the syntax would be slightly different, would be like this. But there's also zeros like, and there's also empty and empty like. So the difference is that, for example, if I take NP zeros, it fills up the matrix with zeros. If I use zero like, then it just fills up the matrix with whatever it has in the memory right now. And that actually saves some time. So it speeds up the code a bit. I'm not sure whether it's relevant in this case, but you can keep that in mind. So empty like, zero like is a bit faster because it does not allocate specifically zeros or whatever as an entry for the matrix. It just takes whatever is just current, which is just available in the memory, and therefore the whole process is a bit faster. So that's the backward part from for the softmax layer. So we have the inputs that we want to pass on to the layer which is above this layer. We receive the outer derivative from the layer which is below the current layer. So we also then run over the different observations, calculate the Jacobian matrix to just make sure that the shape fits, and then multiply the Jacobian matrix with the outer derivative. All right, so that is the part about the softmax layer. And now we want to go back to the entropy layer, this part here, which still doesn't have the backward part, but we also want to include the backward part here. So we just add the backward part. Find it, of course. And it's a new method. And let me also just increase that a bit. And maybe we'll leave one more line space here. So that's the backward part. Again, we need the keyword self to refer to its own class. Then we will have the values. And we will have the true value of y. And that's what we discussed a few slides ago. So we just have to calculate a derivative, the inner derivative from the entropy part, which was the ratio between the true values, the true class assignment, and the values, which in this case will then come from the softmax layer. So the first step that we're going to perform again is to check if the length of the shape of y true equals 1. Then we have a sparse vector. And again, we should be careful with that because of the different versions of the shape a row vector or a column vector can have. So I also would include this here in the comments. And then if we want to compare the output from the softmax layer, so I want to show this again. So the output of the softmax layer is such a matrix. Okay. To the predicted, so the output of the softmax layer to the actual classes, then one idea is actually to compare this matrix directly to the one hot encoded version of the sparse vector, if it's a sparse vector. And that's why we want to turn this vector into a one hot encoded matrix. I showed you an example how to write a little function to turn this vector into one hot encoded matrix. And you could actually do that here. So you can actually call this function and just run it. And call this always in the backward part. However, in this case would be very inconvenient, and there's actually a more efficient way how to do that, and that's by using NPI. I want to quickly show you that. So NPI is a function that creates a diagonal matrix of a certain size. So for example, if it's 3 different classes, then you will get a 3 times 3 identity matrix. Then you can use your vector y for creating a one-hot encoded matrix. So the way you do that is then just say NPI, and then again just index over this vector, and then you have one hot encoded, and that's what we want to do here. So we just want to say then y true equals NPI, and then of course we have to say how many classes we have, and we can also do this with epsilons. With y we can say, okay, we just say d values, and we just get one particular row and determine the length. Then we have the number of classes, and that's the number of labels, so n labels. Which is the number of classes, so it's the same thing. So then we know how many labels we have, right? We know how many labels we have. Then we index this with y true. That generates our one hot encoded vector matrix, or one hot encoded matrix. And then we just calculate the derivative. So we just say self the input. And again, the input is the input for the layer which is above the current layer. And in this layer above the current layer, it will be d values. Again, just passing on the derivatives. And what was the derivative of the entropy? It was just minus y true divided by the d values. That's just the derivative. And we also want to normalize this with n samples. So we also have to calculate n samples or determine n samples before. Also here in the textbook, it just says length, but I also want to be more careful with that. I would just determine the shape first, and we can do this with d values. And then we have n samples, and that's just the derivative of the entropy part. So then we have the backpropagation part from the entropy, and we have all the backpropagation parts. So this is from calculating the cross entropy. This is calculating the loss. So we don't need a backpropagation part because it just has the calculate method. Then we have the backpropagation part for the softmax layer. We have backpropagation for ReLU and for the dense layer. So for everything, we now have the backpropagation part. And therefore, if there's no typo, it should work. And we could in principle run our code already. However, there's one more thing I would like to add, which is also done in the textbook. And so if you look at our function or code snippet where we just test our network, then we call the softmax here. And then we also call, and then we also want to calculate the cross entropy term, and we also want to calculate the prediction. And in principle, we always want to do that anyway. So we always want to call the softmax layer because we want to have the probabilities, because we want to measure the accuracy. And of course, we always want to also calculate the loss, and therefore we need the class which calculates the loss from the loss function. So we have to do those things all the time anyways, and therefore it actually makes more sense to put this in an own class where we just call these two functions here. So where we call this function for calculating the cross entropy, and where we also call this function where we calculate the probabilities from the softmax layer. So we have to do these two things anyways, and therefore why not just calling or creating a class and just calling this class, which calls both of the other classes. And that's what I want to do now. So I want to just set up another class, and we want to just call it calculate softmax loss. And we also want to calculate the gradient. And in this case, the gradient refers to the difference between the predicted probabilities for every class and the actual class assignment. So we need an init part. So we first define our init method. And in this init method, we just call these different classes. So first of all, we have to call the activation softmax. So this is this part, and we're not going to need this in our main function here anymore, so I can remove it. And we just call it here. And then we just call the softmax layer, and we don't need to call it activation anymore. So we just call it activation, and of course self it. So then we just call this part here, which also would change this here. We don't need this part, and it also would change this here. So let's uncomment this for now. So of course this would not work now. We have to add a few more things, but just that you see what we don't need to call anymore. So that's the softmax layer. But now we also want to call this function here, or this class, and we want to just call this self loss. And that's when we just call this part here. All right, so now we define our forward method. So we want to just calculate the loss, and we want to calculate so we want to calculate the loss, and then also we and therefore need the probabilities from the softmax. So we just say self, and then we need the inputs and the true value of y. So what is the inputs here? So maybe you should write a note, because now we're calling these two functions. So what would we do in practice? So we would call, so we would take the output from the last layer and feed it into the softmax layer in order to calculate the probabilities. And based on the probabilities compared to y true, we can calculate the loss. So the inputs here is actually the output from the last layer. And maybe you should write a note. So output from the last dense layer. So that would be the output from this layer here. It generates an output, and we need to feed it into the softmax function. So the inputs is the output from the last dense layer, and therefore we now call our self activation. And that has an input, a forward part, that has a forward part. And in this forward part, we feed in the inputs. So then internally, it calculates the probabilities. So we just say self output. And that is the output from the softmax layer. So that's self activation output. So that creates the output, and these are the probabilities. And later we also want to compare these probabilities with the true values. So these probabilities here with the true values. So we need it for calculating the derivative from the entropy, and we also need it then later to calculate the gradient, so the probabilities, the predicted probabilities versus the actual class assignments. And you see in a few lines. So this is the output from the softmax layer. And with this, we can go into the loss function. And remember, the loss function calculates the loss from the cross entropy, and it calls loss, which has the calculate method. So it will inherit the calculate method. So we can just say calculate. And what does calculate need as an input? Well, since it's called here in the forward method of loss category cross entropy, it needs the predicted probabilities and the true class assignments. So this will be just self output because these are the predicted probabilities. And it, of course, needs the true class assignments. And in principle, we can return this as an output now. So that is the forward part of our combined class, which combines the softmax and the loss calculation. So now we have the loss, and we needed the loss as an output. So in the earlier slides, we had the loss here as an output. And now we want to compare the predictions with y, and that gives us a gradient then actually. So the gradient is the difference of the probabilities. And this will be the backward part. So we self it again. So we have use self. And now we feed in the d values and y true. So the d values, now we have to be careful because we are at the end of our network. So there is no layer below this. So what is the d values then? So the d values are the predicted probabilities from our softmax layer. Because at the end, what we want to compare for the accuracy is this difference here. And this difference has to be minimized. So the accuracy gets maximized. So we have to feed this output as the values. So it's actually this time not a derivative into our calculate softmax loss gradient method or class. So we have to calculate the difference between the predicted values and the class assignments. So how do we do that? Let me therefore just go back to the PowerPoints. So we have our function here. And now we feed in the backward part the values. And that's the output from the softmax layer. Again, we have to make sure that we have the correct orientation, the correct encoding of our classes. And now we want to do the following. So you want to use y true for indexing the d inputs. So we just look at the value we got from the predicted probabilities at the exact current at the correct class. And then we subtract the value 1. And that gives us the gradient. Why is that so? So these are the predictions from the softmax layer. That's the true class assignment. In an ideal world, this 0.7 here would be a 1, because there's a 1 as well, because that's this particular class. So if we subtract 1, so if we have 1 minus 1, then the gradient, the d inputs, is 0. That's perfect, because when there's a 1 here and when there's a 1 here, well, we assigned the class correctly, because then the correct class has the highest probability, and this probability is exactly 1. So here it has the highest probability as well, but if you subtract 1, the difference is 0.3, so the gradient is still not 0. And the same, of course, applies for all the other values here. So the idea now is that we use our y_true vector again for indexing our d inputs, and our d inputs are generated from the d values, which is the probabilities from the softmax layer. So because we have the d values copy here, and then we use y_true for indexing, then we know the assigned probability for the actual class, and then we can calculate the gradient, which is the difference between the value here and the value here and the value here. So that's why it's -1. If the one-hot encoding was not the one-hot encoding, so for example, it's all 2s, then of course there has to be a 2 here. So that's another kind of hard-coded thing. So we assume that if there's an encoding in a matrix, it's always a one-hot encoding. And that's actually pretty much it. So then we have this gradient here and our backward method, and then we can feed this gradient to the layers which are above this particular last layer. So let's just include these 2 or 3 lines of code in the backward part. So we first of all want to determine the number of samples. So we can also just copy and paste this here. So the number of samples is then again d values shape, and then that's the number of samples. And then we want to make sure that our class vector, sparse vector, has the right orientation, so we can use it for indexing. So if length y_true shape equals 2, then we have one hot, which we don't need to. So then we have to sorry, there was something wrong with the speaker. Okay, so we have to so if our class assignment, true class assignment, is a one-hot encoded matrix, then we have to turn it into a vector again in order to use it for indexing. So we say y_true equals, and then we just look for the maximum. So for the index where the maximum is, we just say argmax y_true axis equals 1. Y-axis equals 1. Again, we want to have the maximum for every row along the different columns. Then we have the index, and this index just automatically returns then our sparse vector with the true class assignments. And we want to create the inputs, and the inputs come from the values, which is the probabilities from the softmax layer. So we just copy that. Be careful, just close the brackets because they call an instance. So otherwise you would get probably a weird error message. So we have the inputs, and now we calculate the, so that's not in the loop. And then we calculate the gradient. So we just say self the inputs. And if we just go into range and samples, and then y true, which is now a vector in any case, then we just change the gradient. We're saying -1, and then we just divide by the number of data points, which gives something like an average gradient. All right, so that's the backward part. Let me just test run everything. We're just, yeah, we're working on that. All right, so let me just compile again the network. So the module works, and now we just add what we have set up. So we just add now the new class, because we don't need to do this anymore. And then we can also add the backward part. So we don't need this part here anymore. So we just say now, we just call the activation from which calculates the softmax and the gradient from the loss function. And let me therefore just call the network again, because then it should pop up in the autocomplete. So we just say calc softmax grad, and we just call this like loss function. So this is our loss function. So that is the same structure here. The forward layer, the forward part of the first dense layer passes on the information to the activation, and that passes on the information to the second dense layer, and this creates now an output. But this output does not go into activation 2. Instead, this output now goes directly in our loss function. And in the forward part of the loss function. Because what will happen there, it goes to the forward part. So again, input, it was the output from the last dense layer, so that makes sense. And then it calculates our loss, because it is calling the softmax layer here. Then the softmax layer creates an output, and we use this output in our calculate method, which we got from loss. So where we just calculate the loss, and the loss is just a number. So that's one thing we should check, that we really just get a number and not a vector. So that gives us the loss. And of course, when we look in our new method or in our new class, we also need y true as an input here. So we have to include y as another input, and that creates or calculates our loss. And then we can still calculate the predictions. And we have done this with the activation 2 output. But now we can do this with the output from our loss function. Again, we just go back and we see it creates the self output. That's what we implemented here, which is the output from the softmax. So we can just directly say loss function dot output. So we have all combined. So we get it all at once. Okay, so let me just quickly run this. So we call our network, then we set up the two dense layers, then the redo activation, then our new loss function, and then this structure is already known, and now we should get a loss, which should be 1 point something, so that should be just a number. And let's take a look at this. Yeah, so that's our loss. And now we can also calculate predictions from the output. And that should be something like, so the accuracy should be like a third or so. Yeah, pretty much. Okay, so that is the forward part. But now we calculated, or we set up all the backward methods. So how does it work now? So we want to calculate the gradient between the predictions and actual y. And that was in the backward method of our new class. And we want to calculate this here. So therefore we say loss function backward, and we feed in the d values, which is the output from the loss function. And then we have y here. So that creates the d values, or the d inputs, which will be the d values for the layer which is above this. So let me just run this. And now we should have in our loss function a d input part. And this goes into our last dense layer in the backward method. So these are the d values for the for the layer which is above that. So in the backward part, the whole process is reversed, of course. So then we first have the loss function, then we have the second dense layer. So we just say loss function, the inputs, and we feed this into our dense layer. So the dense layer now calculates internally the change of, so the required change of the bias and the weight. So there should be a d bias and there should be a d weights. So that tells us how we should change the weights and the bias in dense layer. But that's the second dense layer. So it also gets input from the layer above. So it should also have a d inputs. And we're going to put this in the backward part of the layer that would come next, and that's the activation 1. So that's the redo. So we just write activation 1 backward. Again, it requires the d values, which is the d inputs from the layer before. So which also creates the inputs. And we're going to put this into the backward part of the first dense layer. And therefore, also the first dense layer, it should have calculated now the d values. So like the weights and the biases. And also check the dimension of that. So if we run it completely, then, and if we just enter that with a certain number of neurons, it also should have a certain number of neurons. So let me therefore check this, because this for our spiral data set. Then we have 3 classes in where we want to calculate the probability. So this value has to be 3, and this value can be anything. So let me just run this here, and we check for the dimensions. So we just say dense 1, and then we have the d-biases, and we have dense 1, and then have d-weights. And if you actually look at this, and if you look at x, it fully makes sense, right? Because we have 2 features, right? So we have 2 inputs, so to say, and for 5 neurons. Why do we have 5 neurons? Well, that's what we said here. Then in the second dense layer, so if we just take a look at the weights shape from the second, we feed in with 5 neurons, so we have 5 features. That makes sense. And then we have 3 output neurons, so we have 3 classes because we have 3 output neurons. It also makes sense. So these weights are for the 5 different neurons, and they have 3 each. And the output here, then we have an output with of the length 3, which corresponds to the 3 classes. And we can also check again the loss function output should have the shape then 600 times 3, because we have 600 observations, and we have 3 classes. So just from the shape of the matrices, that all makes sense. And what we could do in principle now is we can try to optimize our loss and our accuracy by doing the following. So in principle, we could now say, okay, we know the weights. So for example, let's go to dense 1 weights. And according to our gradient descent method, we actually know how to change this, because now we know the change of the weights, the derivative d weights. All right, and we multiply this with a small negative constant, so the negative is already here, and then change the weights accordingly. And then we can also do this, for example, with the weights for the other dense layer, and we can also do this with the biases. And of course, we have to say the biases. And that would actually, if we just run this all over all the time, then it should actually ideally improve the accuracy. So in principle, if we just say for I in range, like say 1000 or so, then it should actually improve our accuracy. So if we just do this here within a loop, then if you just print the accuracy, then it should improve the accuracy, and by continuously improving the weights and the biases, and kind of if you do that, accuracy actually should go up. So I did it for a few iterations. It went up from 0.3 or so to 0.43, and so therefore it's actually learning already, and it's improving the weights, it's minimizing the entropy, and it's optimizing, so increasing the accuracy. And that would kind of work already. So our network now is able to learn, but it's a very, let's say, unprofessional way how to do that. So what we will do next is, and that is the part of the next chapter. So let me just go to the PowerPoint. So what we do next is to automate this process, and it's called optimization. So we want to set up a new class which changes the weights and the biases accordingly. And we also want to add a few more features. For example, what you have seen here now is just having particular learning rate, which is something like 0.01. And then somehow it works already. But we also want to take into account, for example, that the learning rate can be changed. So for example, we start at a large learning rate, so it learns faster, but then the learning rate should decrease, because if we get closer to a minimum, we want to avoid to miss it. And if the learning rate is too large, the step we take in the gradient descent might be too large, and we just miss the minimum. But on the other hand, we also want to avoid that our algorithm or optimization process gets stuck somewhere in a small local minimum. So we also have to take into account something like the overall shape of our loss function. And we want to put all of this in the so-called optimizer. So we want to run an optimizer and then run this optimizer on our network. And this will be the next chapter.